triangle AB0C0 has side lengths AB0 equals 12, B0C0 equals 17, and C0A equals 25. For each positive integer n, points Bn and Cn are located on ABn-1 and ACn-1 respectively, creating three similar triangles ABN-Cn, Bn-1 Cn-Cn-1, and ABn-1 Cn-1. The area of the union of all triangles Bn-1 Cn-Bn for n is greater than or equal to 1 can be expressed as P over Q, where P and Q are relatively prime positive integers. Find Q. This is triangle AB0C0, which has side lengths 12, 17, and 25. And we know that triangle AB0C0 is an obtuse triangle because the sum of the squares of its two shortest sides, 12 squared plus 17 squared, is less than the square of its longest side, 25. 12 squared is equal to 144, 17 squared is equal to 289, so their sum is equal to 433, and that is less than 625. So we have the triangle AB0C0 is obtuse. We would like to add points B1 and C1 on AB0 and AC0 respectively, such that these three triangles are all similar to each other, where n is equal to 1. So we have triangle AB1C1 is similar to triangle B0C1C0 is similar to triangle AB0C0. The first triangle being similar to the third simply means that B1C1 is parallel to B0C0. So we can draw them like this. I'll put B1 there and C1 there on AC0. But also B0C1C0 is similar to AB0C0. So let's draw that. That's this triangle here. And it is similar to AB0C0, so we can write down some angles. We need this one to be equal to angle A. This one needs to be equal to angle B0, and this is obviously C0. Now we have just built layer 1, the lowest layer of this repeated sequence. We can now build layer 2 in triangle AB1C1, just as we did layer 1 in AB0C0. To start building layer 2, we can draw the line from B1 out to AC0 like this, such that this angle remains A, and I'll call that point C2. Then we can draw a line out west to AB0 that's parallel to B0C0 and B1C1. That's B2. So this is layer 2, and this is a sequence that goes on and on and on. We just want to find the area of the union of all triangles Bn-1 Cn-Bn. So that starts with B0, C1, B1. I'll shade that in dark blue. It starts with this triangle, and it goes on with this triangle, and so on, all the way up to A. If we want to find the area of all triangles Bn-1 Cn-Bn for n is greater than or equal to 1, we have to focus on the ratio of the sum of the areas of all those triangles to the area of triangle AB0C0. So we have that all the layers are similar by similar triangles, and that means that the areas of the left triangles in each layer, whose areas we're summing, will have a constant ratio relative to the area of the whole layer. So what this means is if we were to take layer 1, the triangle to the left in that layer is B0, C1, B1. And the ratio of the area of that triangle to the area of layer 1 is equal to the ratio of the area of B1, C2, B2 to the area of layer 2. And this ratio is the same for all layers. It goes on and on and on. Let's call this common ratio R. Then all layers, the sum of all layers is just triangle AB0C0. So we just want the area of triangle AB0C0 times R for the area of our union of all triangles Bn-1 Cn-Bn. We will focus on only the lowest layer to find R. So in the lowest layer, note that angle C0, B0, C1 is equal to angle A. So we actually have that C0, B0 is tangent to the circumcircle of triangle AB0, C1, because both of these angles are equal to A. So by power of a point, we can actually find C0, C1. And we have C0, B0 squared, which is 17 squared, and that's equal to 289. It's equal to C0, C1 times 25. And so we have C0, C1 is equal to 289 over 25. So we can write here 289 over 25. And that leaves AC1 equal to 336 over 25. This makes it easier to find the area of the union over the area of AB0C0, since, as we said earlier, that is just the area of B0C1B1 over the area of layer 1. And that can be found easier now that we know these lengths. We have that this is equal to the area of B0C1B1 over the area of that triangle plus triangle B0C1C0. Let's call the area of triangle B0C1B1 x. Then we would like x over x plus the area of B0C1C0. Let's compare the triangles. Well, first of all, they have the same height. That is the distance between parallel lines B1C1 and B0C0. But they have different bases. And that is the ratio. We need to find the ratio between B1C1 and B0C0. X plus x times B0C0 over B1C1. Because x was the area of triangle B0B1C1, which had a base B1C1, but the other triangle has the base B0C0. That's why we're multiplying by this scale factor. And that's just equal to, by similar triangles, that's just equal to x over x plus x times AC0 over AC1. That's just 25 over 336 over 25, which if you multiply both by 25, you get 625 over 336. And this is equal to, if you cancel the x, if you divide both numerator and denominator by x, you get 1 over 1 plus 625 over 336. And that is equal to 961 over 336. You get 336 over 961. And that is equal to the area of the union U divided by the area of triangle AB0C0. So we found our R equals 336 over 961. All that's left is to multiply that ratio by the area of triangle AB0C0. Let's find that. It has side lengths 12, 17, and 25. We can use Heron's formula. The semi-perimeter is 12 plus 17 plus 25 over 2. And that's 54 over 2, which is 27. And then 27 minus 12 is 15. 27 minus 17 is 10. And 27 minus 25 is 2. This is equal to the square root of 405 times 20, which is the square root of 8100. And that's equal to 90. So we have R equals 336 over 961. And we want to multiply that by 90. So we have the area of the union U is equal to 90 times 336 over 961. And this can be expressed as P over Q, where P and Q are relatively prime positive integers. P is 90 times 336, and Q is 961. Thank you for watching my YouTube video, and please follow my channel if you would like to see more videos.